What if I told you there's a place where the laws of physics seem to bend, where time stretches like taffy, and where entire galaxies vanish without a trace? This isn't science fiction, it's the universe we live in. Right now, as you sit there, black holes are devouring stars, dark energy is pushing the cosmos apart, and somewhere out there, planets might harbor life we can't even begin to comprehend. Yet for all our telescopes, probes, and brilliant minds, space remains the greatest mystery of all. We've walked on the moon, mapped distant worlds, and peered back to the dawn of time itself, but the more we learn, the more we realize how much we don't know. Think about this: every single star you see at night is a question mark. Somewhere among them, there could be answers to secrets that have haunted humanity for centuries. Are we alone? What's at the edge of the universe? Why does 95% of it seem to be made of something we can't see or touch? These aren't just science problems, they're riddles that tug at our very existence. And here's the wildest part: some of these puzzles might never be solved, not because we aren't smart enough, but because the universe seems determined to keep its deepest truth just out of reach. That's where this journey begins. Over the next 30 questions, we're diving into the cosmic unknown, the gaps in our knowledge that even the sharpest astrophysicists lose sleep over. From the eerie silence of Fermi's paradox to the ghostly whispers of dark matter, these aren't just trivia tidbits, they're the boundaries of human understanding, the cliffs where our curiosity meets the unfathomable. So buckle up, by the time we're done you'll see the night sky differently, because once you stare into these abysses, mystery takes on a whole new meaning. Picture holding a flashlight in a pitch-black room. No matter how bright the beam, most of the space around you stays hidden, just like our universe. We've mapped galaxies, weighed black holes, even recreated cosmic explosions in labs, but there's an invisible elephant in the room: dark matter. This ghostly substance makes up 27% of everything that exists, yet we've never seen it, touched it, or even confirmed what it's made of. It's the ultimate cosmic hide and seek, and we're the ones searching blindfolded. Here's how bizarre this gets: stars on the edge of galaxies rotate just as fast as those near the center, defying gravity's rules, like a carousel spinning so fast the outer horses should fling off, but somehow don't. The only explanation: an unseen force, dark matter's gravitational pull, acting like cosmic glue holding galaxies together. But if it's everywhere, why can't we detect it? Scientists have turned entire mountains into labs, miles underground, hunting for weakly interacting massive particles, wimp hypothetical bits of dark matter so shy they might pass through a block of lead the size of our solar system without a single collision. Then there are actions, particles so lightweight, trillions could be streaming through your hand right now, leaving no trace. The kicker: dark matter might not even be particles at all. Some theories suggest it's primordial black holes, relics from the Big Bang lurking in the cosmic shadows. Others propose we've got gravity all wrong, that our equations need rewriting, not some invisible substance. Every experiment that comes up empty, like dropping a net into the ocean and pulling it out dry, only deepens the mystery. The universe is whispering secrets in a language we haven't quite decoded yet. And until we do, 95% of reality remains a question mark. We might think we've mapped our own cosmic backyard, but the solar system still has a few tricks up its sleeve, like the ghostly presence of something massive lurking beyond Neptune. Astronomers call it Planet 9, a hypothetical world 10 times heavier than Earth, hiding in the frozen outskirts where sunlight is a faint memory. The evidence: a cluster of tiny icy objects in the Kuiper belt, all mysteriously tilted in the same direction, as if an unseen hand is herding them. Their orbits are so stretched and skewed that something big must be yanking them into place, and whatever it is, we can't see it. Could this shadowy giant be a rogue planet, flung outward during the solar system's chaotic youth? A wandering world captured from another star? Or here's where it gets wild: might it not be a planet at all? some scientists have thrown another contender into the ring, a primordial black hole, no bigger than a grapefruit but with a mass of 10 Earths, warping space-time as it drifts through the darkness. Imagine a cosmic wrecking ball so dense, it bends the paths of everything around it, yet remains invisible to telescopes. The hunt for Planet 9 has turned into a celestial game of cat and mouse. Telescopes scan the skies for faint heat signatures, while others look for the occasional flicker of light bending around a hidden mass. Every strange pattern in the Kuiper belt adds another piece to the puzzle. But here's the twist: even if we never find it, the search forces us to rethink what a planet really is. Is it a familiar world like Jupiter, or could it be something far stranger, a relic from the birth of the universe, hiding in plain sight? Until we know for sure, our solar system story remains delightfully unfinished. Here's something that should mess with your sense of reality. The universe isn't just expanding, it's doing so at an accelerating pace, like a runaway train pressing harder on the gas. This wasn't supposed to happen. When Edwin Hubble first discovered galaxies flying apart in the 1920s, scientists assumed gravity would eventually slow the expansion, maybe even reverse it. But in the late 1990s, observations of distant supernova delivered a plot twist. The cosmos wasn't just coasting, it was speeding up. The culprit, a shadowy force dubbed dark energy, making up a staggering 68% of the universe. Think of it as anti-gravity, a repulsive pressure woven into the fabric of space itself. The more the universe expands, the more dark energy there seems to be, creating a feedback loop that could one day tear galaxies apart atom by atom. But here's the catch: no one knows what dark energy actually is. The leading theory points to vacuum energy, a kind of background hum of particles flickering in and out of existence. Yet when physicists crunch the numbers, their predictions are off by a factor of 10 followed by 120 zeros, the worst miscalculation in science history. Not everyone's convinced dark energy exists, though. Some theorists argue we've got gravity all wrong, that Einstein's equations need tweaking on cosmic scales. Modified Newtonian dynamics, or MEND, suggests gravity behaves differently when pulled thinly across vast distances, eliminating the need for invisible forces. But MEND has its own headaches, failing to explain certain galactic motions. Then there's the wild card: what if dark energy isn't constant? Ancient light from the cosmic microwave background hints it might fluctuate, growing stronger or weaker over eons. The stakes couldn't be higher. If dark energy strengthens, it could trigger a big rip, shredding spacetime itself. If it vanishes, gravity might collapse the universe into a reverse Big Bang. For now, telescopes like Euclid and the Vera Rubin Observatory are hunting for clues in the bending of starlight and the clustering of galaxies. But every answer seems to unveil deeper questions, leaving us to wonder: are we decoding the universe's rules, or just glimpsing the edges of our own ignorance? We've all heard the story. 13.8 billion years ago, the universe burst into existence from a single, infinitely dense point. But here's the part that keeps cosmologists up at night: what set it off? What existed before the Big Bang, and does before even mean anything when time itself began at that moment? It's like asking what's north of the North Pole. The rules we take for granted break down completely when we rewind to the universe's first flicker. Some theories suggest the Big Bang wasn't a beginning at all, but a rebound. Imagine a cosmic accordion, cycles of expansion and collapse repeating eternally. In these bounce models, our universe is just the latest in an endless series, crushed down to a hot, dense speck before springing back outward. Others propose a multiverse where our Big Bang was just one bubble in a frothing sea of universes, each with different laws of physics. Picture an infinite ocean where new bubbles constantly form, collide, or fade, some sterile, some stranger than we could imagine. Then there's the quantum twist. At temperatures trillions of times hotter than the core of the Sun, the infant universe was ruled by quantum weirdness. where particles blink in and out of existence and gravity might have behaved like a repulsive force. Some models suggest a quantum fluctuation in a primordial void, a random hiccup in nothingness, spawned everything we know, but even this leaves us staring into the abyss. What created the void? The truth is, our physics hits a wall at the Planck epoch, the first fraction of a second where gravity, relativity, and quantum mechanics all clash. It's like trying to read a book where the first chapter's been shredded, until we find a theory of quantum gravity, a way to marry Einstein's cosmos with the subatomic realm. The Big Bang's origin remains the ultimate cold case. And that's the humbling beauty of it. The universe might forever keep its deepest secret, how it all began. The math suggests the universe should be teeming with life. With billions of galaxies, each containing billions of stars, and countless planets orbiting in habitable zones, the odds seem overwhelmingly in favor of alien civilizations. So where is everybody? That's the unsettling heart of the Fermi paradox, the glaring contradiction between high probability and total silence. Even conservative estimates using the Drake equation, which calculates potential intelligent civilizations, hint at thousands of neighbors across the Milky Way alone. Yet after decades of listening with radio telescopes, SETI has heard only static. Consider this: if just one advanced civilization arose a few million years before us, a blink in cosmic time, they'd have had ample opportunity to colonize the galaxy. Self-replicating probes could spread exponentially, reaching every star within a few million years, so why haven't we found relics, signals, or even faint traces? Some argue we're looking in the wrong way, that advanced civilizations might communicate with lasers, neutrinos, or even quantum entanglement, leaving our radio searches obsolete. Others propose a darker answer, the Great Filter. This chilling idea suggests some catastrophic hurdle: nuclear war, AI rebellion, or environmental collapse wipes out civilizations before they can spread. The question then becomes terrifying: are we approaching that filter, or have we already slipped past it? Then there's the zoo hypothesis, the notion that aliens observe us like animals in a cosmic wildlife preserve, deliberately avoiding contact. Or maybe we're simply too primitive to notice their presence. Imagine ants at the base of a skyscraper, unaware of the bustling city above. UFO sightings add fuel to the debate, but even the most credible cases, like the Pentagon's declassified UAP footage, lack definitive proof. Atmospheric phenomena, secret military tech, or actual extraterrestrial visits, the data remains frustratingly fuzzy, perhaps the most humbling possibility. We truly are alone, that in this vast glittering expanse, life on Earth is a 1 in a trillion fluke, but until we know for sure, the night sky remains an unanswered question, a silent ocean where every star could be a beacon or a tomb. The search continues because the answer doesn't just tell us about the universe, it tells us about ourselves. There's a place in the universe where the rulebook of physics gets torn to shreds, a black hole. Imagine throwing a clock into one. From the outside you'd see time slow to a crawl as the clock approaches the event horizon, that point of no return where even light surrenders to gravity's grip. But cross that threshold, and the clock would be stretched atom by atom in a process scientists call spaghettification, shredded into particles that spiral toward the singularity, a point of infinite density where all our equations crash. A place where space and time cease to exist as we know them. The strangeness only deepens when we ask, what happens to all that swallowed matter? Quantum mechanics says information can't be destroyed, yet black holes seem to erase it permanently. This contradiction, known as the information paradox, had even Einstein and Hawking at odds. Hawking proposed that black holes aren't completely black, they slowly leak energy through Hawking radiation, a quantum quirk where particle-antiparticle pairs form near the event horizon. One falls in, the other escapes, carrying away tiny bits of the black hole's mass over eons. Eventually, the black hole evaporates, but where does the information go? Some theories suggest it scrambled at the horizon like cosmic encryption, while others argue it's funneled into a parallel universe. Then there's the wild card: what if singularities don't exist? Loop quantum gravity proposes a Planck star at the core, a dense remnant that rebounds like a squeezed spring, potentially birthing a new universe. String theory offers fuzzballs, tangled strings of energy with no sharp edges. Even the event horizon might be an illusion, a firewall of searing particles that incinerates anything crossing it. Black holes defy everything. They're cosmic paradoxes, vacuum cleaners that might secretly be leaking, tombs that could be portals. And here's the kicker: we might never know for sure, unless we send a probe into one, and good luck getting a signal out. These monsters will keep their secrets locked behind curtains of twisted spacetime. The only certainty: the closer we look, the more they unravel our understanding of reality itself. Imagine this: a tiny microbe frozen in the icy heart of a comet, hurtling through space for billions of years before crashing into a young, watery Earth. That single spark could have been the seed of all life on our planet. This isn't fantasy, it's panspermia, the idea that life's ingredients, or even life itself, hitched a ride across the cosmos. And the evidence is piling up in the most unexpected places. Take the Murchison meteorite, a space rock that landed in Australia in 1969. When scientists cracked it open, they found over 90 different amino acids, the building blocks of proteins, including some never seen on Earth. Then there's Ryugu, an asteroid sampled by Japan's Hayabusa 2 probe, packed with uracil and niacin, key components of RNA and metabolism. These discoveries suggest the universe might be preloaded with life's raw materials, scattering them like cosmic breadcrumbs. But how fragile could these molecules survive the trip? Laboratory experiments show some bacteria, like Deinococcus radiodurans, can endure years of space radiation by entering a dormant state. Others theorize life's precursors could have been shielded inside comets, protected by layers of ice until they melted in Earth's ancient oceans. The math gets eerie. If just 1 in a million comets carried genetic material, trillions of chances existed for seeding our planet, yet Earth wasn't a passive recipient. Hydrothermal vents with their mineral-rich chimneys might have acted as primordial factories, assembling these space-delivered ingredients into something alive. The debate rages: did life arise here through chemistry, or was it a cosmic delivery? The answer might be both: a collaboration between celestial messengers and our planet's perfect conditions. Until we find life elsewhere, this remains the ultimate cold case, a mystery written in asteroids, comets, and the very cells of every living thing. Somewhere in the vast darkness behind our own Milky Way, an unseen force is reeling in entire galaxies like fish on a cosmic hook. We call it the Great Attractor, a gravitational anomaly so powerful, it's dragging thousands of galaxies, including our own, toward it at over 2 million kilometers per hour. But here's the catch: we can't see it. Our best telescopes stare straight into a blind spot known as the zone of avoidance, a thick shroud of gas, dust, and stars blocking nearly 20% of the sky from our view. It's like trying to spot a lighthouse during a sandstorm. The first clues came in the 1970s, when astronomers noticed galaxies in our local cluster, all streaming toward the same patch of nothingness. Whatever lurked there had the mass of tens of thousands of Milky Ways. Early theories speculated it might be a supercluster, a dense knot of galaxies bound together by gravity. Later observations revealed the Norma cluster at the heart of this anomaly, but its gravity alone couldn't explain the pull. The Great Attractor had to be something bigger, something darker. Enter the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years. Our Milky Way sits on the outskirts of this cosmic continent, and the Great Attractor appears to be its gravitational center, a valley where galaxies slide toward a common point like marbles rolling downhill. But even this revelation only deepens the mystery. Why does the motion of galaxies suggest more mass than we can account for? Some suspect hidden reservoirs of dark matter, or even unseen threads of the cosmic web funneling galaxies toward larger structures we've yet to map. Then there's the wild card, the Shapley Attractor, an even more massive supercluster 600 million light-years beyond the Great Attractor. Like competing tides, both these giants tug at our galaxy, making it hard to tease apart which force dominates. Could the Great Attractor merely be a waypoint on our path towards something far larger, or is it a symptom of something stranger, an imbalance in the very fabric of spacetime left over from the Big Bang? For now, new tools like X-ray and infrared telescopes are peeling back the Milky Way's dusty veil, pixel by pixel. Each glimpse reveals more galaxies, more clusters, yet the full picture stays frustratingly out of focus. The Great Attractor reminds us that even as we map the cosmos, some forces remain hidden in plain sight, ghosts in the celestial machine, pulling strings we're only beginning to sense. At the birth of the universe, matter and antimatter should have cancelled each other out in a blaze of mutual annihilation, leaving behind nothing but pure energy. Yet here we are, in a cosmos brimming with galaxies, planets, and people. This is the Barrian asymmetry problem, one of physics' greatest unsolved puzzles. Why does anything exist at all? The math says the Big Bang should have produced equal parts matter and antimatter, their collisions leaving no survivors, but for every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny imbalance, 1 part in a billion, is all that stands between us and oblivion. To understand how bizarre this is, imagine flipping a coin 1,000,000,000 times and getting heads just once more than tails. That's the level of luck we're talking about, except the universe doesn't run on luck. The answer might lie in a subtle cosmic favoritism called CP violation. In particle physics, C stands for charge swapping particles with antiparticles, and P for parity mirroring their behavior. For decades, scientists assumed these symmetries were perfect, that antimatter should behave exactly like matter in a mirror universe. But in 1964, researchers studying kaons, exotic subatomic particles, found a crack in the mirror. These particles decayed slightly differently from their antimatter counterparts, violating CP symmetry. That discovery earned a Nobel Prize, but the effect was far too weak to explain our matter-dominated universe. Enter CERN LHCb experiment, where physicists smash particles at near light speeds to recreate the early universe's conditions. They've found more CP violations, particularly in beauty quarks, yet the numbers still don't add up. Even combined, these quirks account for maybe 1% of the matter-antimatter gap. So where's the rest? Some theories point to neutrinos. These ghostly particles, which barely interact with matter, might flip between matter and antimatter states asymmetrically, a process called leptogenesis. Others suggest undiscovered particles, like hypothetical actions, tip the scales during the universe's first microseconds. Then there's the radical idea that antimatter didn't vanish, it's hiding. Could entire antimatter galaxies lurk beyond our observable universe? The Alpha experiment at CERN traps anti-hydrogen atoms in magnetic bottles, studying whether they obey gravity's rules or fall up. So far, no dice, but if antimatter does behave differently, it might have been pushed to cosmic fringes during the Big Bang's violent expansion. The stakes are cosmic. Solving this riddle wouldn't just explain why we exist, it could reveal new laws of physics, hidden dimensions, or even clues about the universe's ultimate fate. Until then, every atom in your body is a relic of that ancient mysterious imbalance, 1,000,000,001 bet that somehow paid off. One moment there's silence, the next, a blast of radio waves brighter than 1,000,000,000 suns floods the cosmos, then vanishes without a trace. These are fast radio bursts, or FRB, some of the most enigmatic signals in the universe. Lasting just milliseconds, they pack more energy than our sun emits in decades, and they come from galaxies so far away, their light has traveled billions of years to reach us. The strangest part, most erupt once and never repeat, like cosmic firecrackers with no fuse to trace. The first FRB was discovered in 2007, buried in old telescope data, a spike so intense, astronomers initially dismissed it as equipment glitch. Then came the repeater, in 2016, a signal named FRB 1211, stunned scientists by flashing over and over from a dwarf galaxy 3 billion light-years away. This wasn't a one-off explosion, something out there was persistent. The leading suspect, magnators, the zombie stars of the cosmos. Born from supernovas, these neutron stars spin wildly, wrapped in magnetic fields so intense, they could strip atoms apart from 1,000 kilometers away. Theorists suggest starquakes on their surfaces or magnetic snap and reconnect events might unleash these radio tsunamis, but not all FRBs fit neatly into the magnetar box. Some pulses arrive with bizarre substructures, tiny chirps, and splits within the main burst hinting at environments so extreme, even magnetars might struggle to explain them. Then there's the elephant in the room, FRB 2020, a signal from our own galactic backyard, emanating from a known magnetar. While this confirmed a natural origin for at least some bursts, it deepened the mystery of why others seem to originate from entirely different cosmic neighborhoods. And yes, aliens have crossed scientists' minds. The repetitive patterns of certain FRBs, like the famous every 16 days cycle of FRB 1809 fuel speculation about artificial beacons or propulsion systems harnessing unimaginable energy. But Occam's razor leans toward nature's creativity over extraterrestrial engineering. One wild theory involves blitzars, supermassive neutron stars that collapse into black holes mid-spin, releasing their energy in a final, screaming radio pulse. Others propose cosmic strings defects in spacetime from the Big Bang vibrating like plucked guitar strings. The hunt for answers is accelerating. Telescopes like CHIME in Canada now catch dozens of FRBs monthly, mapping their locations across the sky. Each new detection peels back another layer, revealing twists like polarized waves that suggest tangled magnetic fields at the source. Yet for every clue, a dozen questions sprout. Are FRBs the universe's way of signaling catastrophic stellar deaths, or are they cosmic lighthouses, illuminating the invisible gas between galaxies? One thing's certain, in the crackle of these fleeting signals, the cosmos is whispering, and we're just learning how to listen. Time isn't the rigid, unchanging river we experience, it's more like a stretchy fabric, bending under the weight of stars and black holes. Einstein's theory of relativity shattered the idea of a universal clock, proving time slows near massive objects or at high speeds. But if time is flexible, could it bend so far that it loops back on itself? The equations say yes. Wormholes, cosmic shortcuts through spacetime could, in theory, connect distant moments as easily as they connect distant places. Picture folding a piece of paper so 2 points touch. A wormhole would be the needle punching through. If one end moved near a black hole where time crawls, and the other stayed in normal space, stepping through could send you to the past. But here's where logic unravels, the grandfather paradox. What if you traveled back and prevented your own birth? Is just the start. Quantum mechanics offers wild workarounds. The many worlds interpretation suggests every decision spawns alternate timelines, so changing the past wouldn't erase your future, just branch you into a new one. Then there's the self-consistent model, where the universe conspires to prevent paradoxes. Try to shoot your grandfather, and the gun jams because you must exist to pull the trigger. Reality might already hold clues. In 1874, physicist Frank Tipler proposed a rotating cylinder so dense and fast, it would twist spacetime into a closed time-like curve, a path where time circles back. Quantum particles hint at stranger possibilities. Experiments with time crystals, structures that repeat in time like diamonds, repeat in space, show matter can exhibit behaviors that defy classical time's arrow. Yet practical time travel faces brutal hurdles. Wormholes demand exotic matter with negative energy to stay open, a substance we've only glimpsed in quantum foam. The energy needed to twist spacetime might exceed all the power in the universe, and then there's causality, the cosmic guardrail that keeps effects from preceding causes. Break it and the universe might simply refuse to compute. So is time travel possible? The laws of physics don't say no, but they whisper warnings in the equations. Every theoretical loophole comes with a cosmic asterisk, a reminder that time's secrets are guarded by paradoxes and probabilities. For now, the past remains locked away, not by impossibility, but by the universe's stubborn insistence on making sense. Imagine crushing the entire mass of our Sun into a sphere the size of Manhattan. That's a neutron star, a cosmic diamond forged in the heart of a supernova so dense, a single teaspoon of its material would weigh billions of tons on Earth. But what lurks beneath its surface is even stranger than the numbers suggest. At these extreme pressures, atoms themselves cease to exist, electrons are smashed into protons, forming a sea of neutrons so tightly packed, they behave like a single quantum liquid. Yet this is just the outer layer. Venture deeper, and matter might dissolve into something even more exotic, a state that hasn't existed since the universe's first microseconds. Scientists call it quark-gluon plasma, the primordial soup that filled the cosmos right after the Big Bang. Normally, quarks and gluons are forever locked inside protons and neutrons by the strong nuclear force. But under the unimaginable crush of a neutron star's core, these particles might break free, swirling in a frictionless superfluid. Some models suggest this quark matter could form bizarre configurations, strange stars made entirely of strange quarks, or crystalline structures where quarks arrange themselves into geometric lattices. Then there's the pasta phase, not a cosmic kitchen accident, but layers of neutron-rich material squeezed into shapes resembling spaghetti, lasagna, or even waffles, their density warping spacetime like tiny gravitational lenses. But how do we study something we can't touch? The answer lies in starlight. When neutron stars collide as observed in the gravitational wave event GW 170817, their explosive mergers spray heavy elements like gold and platinum into space while offering a fleeting glimpse of their interiors. Telescopes detected a telltale delay in the gamma-ray burst that followed, hinting at an ultra-dense, slow-to-deform core, possibly made of quark matter. Meanwhile, a NASA NICER mission maps the size and mass of neutron stars by studying X-rays emitted from hotspots on their surfaces. A slightly larger star might hint at softer quark goo interiors, while a smaller one suggests a stiff crust of pure neutrons. Yet mysteries remain. If quark matter exists inside these stars, why haven't we spotted a quark nova, an even more explosive sibling to a supernova? Could some neutron stars actually be quark stars in disguise, their true nature hidden beneath a thin veneer of ordinary matter? And what happens when pressure surpasses even quark degenerate limits? Some theories propose a collapse into a black hole, while others suggest a transition into preons hypothetical particles even smaller than quarks. The core of a neutron star is a laboratory unlike any on Earth, where matter is pushed to its quantum edge. Every new observation peels back another layer, revealing a world where the familiar rules of physics twist into something alien, and where the universe's most extreme conditions might still be hiding surprises. A star's death is anything but peaceful. Its final moments are a spectacular battle between gravity and nuclear fire, and the outcome depends on a single, critical factor: mass. Take two stars from the same stellar nursery, and one might end its life in a brilliant supernova, while the other vanishes silently into a black hole. The difference, a cosmic tipping point hidden in the equations of physics. For stars like our Sun, the end is relatively quiet. After billions of years fusing hydrogen into helium, they swell into red giants before shedding their outer layers as glowing planetary nebulae, leaving behind a dense, Earth-sized ember called a white dwarf. But add more mass to the equation, and things get explosive. stars 8 times heavier than the Sun or more face a far more violent fate. Their cores become layered like an onion, fusing heavier elements until they reach iron, the cosmic dead end. Unlike lighter elements, iron fusion absorbs energy instead of releasing it, cutting off the star's power supply. In an instant, gravity wins. The core collapses at a quarter the speed of light, cramming a sun's worth of mass into a sphere no bigger than a city. The outer layers, suddenly without support, rebound off this ultra-dense core in a shockwave that rips the star apart, a core collapse supernova, so bright it can outshine an entire galaxy. But there's another, stranger way for stars to explode. Imagine a white dwarf, the leftover core of a sun-like star stealing matter from a companion star. As it gorges itself, its weight creeps toward a critical limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. At this threshold, the dwarf's carbon-rich core ignites in a runaway fusion reaction, detonating like a thermonuclear bomb. This is a Type Ia supernova, so uniform in brightness that astronomers use them as cosmic yardsticks to measure the universe's expansion. Here's where the cosmic fork in the road appears. For the collapsing cores of massive stars, the aftermath depends on how much material remains after the supernova's fury. If the core weighs between 1.4 and roughly 3 solar masses, it crushes down into a neutron star, a pulsating magnetized orb so dense, its gravity bends light into a halo. But push past 3 solar masses, and no known force can stop the collapse. The core implodes into a black hole, swallowing even the evidence of its own birth. Yet mysteries linger. Some supernovae are oddly dim, while others, like SN 2006 Gi, shine 100 times brighter than expected. Could there be stars that bypass supernova entirely, collapsing straight into black holes without a fireworks display? And what about hypergiants like Eta Carinae, teetering on the edge of explosion for centuries? The universe keeps its death rites unpredictable, reminding us that even the laws of physics have room for surprises when stars reach their breaking point. On the night of August 15, 1977, a radio telescope in Ohio picked up a signal so bizarre, an astronomer scrawled, "Wow," in the margin of the data printout, and the name stuck. For 72 seconds, the Big Ear telescope detected a narrowband radio burst at 1420 MHz, matching the predicted signature of an artificial transmission from deep space. It came from the direction of the constellation Sagittarius, near a star cluster 180 light-years away, and then, nothing, no repeats, no echoes, just silence. What made the wow signal so extraordinary wasn't just its strength, 30 times louder than cosmic background noise, but its frequency. Hydrogen, the universe's most abundant element, naturally emits radio waves at 1420 MHz, making it a logical hailing frequency for any civilization trying to announce its presence. The signal also fit the expected profile of an interstellar beacon, narrowband meaning finely tuned and undrifting, locking onto a precise frequency without wobble, unlike natural sources affected by planetary motion. Yet despite decades of follow-up scans, including targeted searches by the SETI Institute and amateur astronomers worldwide, the signal never reappeared. Skeptics have proposed natural explanations. Could it have been a reflected terrestrial transmission bouncing off space debris? Unlikely. Human tech in the 70s rarely operated at that exact frequency. A passing comet, the signal's fixed position rules out objects moving through the solar system. Some suggest an unknown astrophysical phenomenon, like a never-before-seen flare from a neutron star or a fortuitous alignment of interstellar plasma acting as a cosmic lens. But none fully explain the signal's artificial-seeming precision. Then there's the tantalizing possibility we're not meant to find it again. If the signal was a one-time beacon, a deliberate directional pulse aimed briefly at Earth, its purpose might have been to get our attention, not sustain a conversation. Imagine a lighthouse sweeping its beam across the ocean. By the time you see it and wave back, the light has already moved on. The wow signal endures as a cosmic Rorschach test. To some, it's proof we're not alone. To others, a reminder of how easily nature can mimic intelligence. Until another signal arrives, one we can verify, it remains the universe's most provocative unanswered call. Look up at the night sky through a telescope, and you'll find galaxies in all shapes and sizes, some like swirling whirlpools, others as smooth as footballs, and a few that look like they've been thrown into a cosmic blender. How does something as massive as a galaxy, with hundreds of billions of stars, settle into these distinct forms? The answer lies in a delicate dance between gravity, dark matter, and violent collisions that play out over billions of years. Take spiral galaxies like our Milky Way. These cosmic pinwheels are star-making factories, with graceful arms winding outward from a bright central bulge. Their shape comes from motion stars and gas orbit the center, but not in perfect unison. Denser regions rotate slightly slower, creating a traffic jam that compresses gas into glowing arms where new stars ignite. Dark matter's invisible halo likely acts as scaffolding, guiding this rotation, yet spirals aren't eternal. Over time, their gas gets used up in star formation, or stripped away by intergalactic winds, leaving them quieter and more diffused. Then there are elliptical galaxies, the universe's retired giants. These featureless orbs, packed with older, redder stars, resemble glowing embers. Unlike spirals, their stars don't orbit in an orderly disk but buzz around like swarms of bees, a sign of a chaotic past. Most form through galactic mergers where two spirals collide. When galaxies smash together, their stars rarely hit head-on. Space is too vast, but their mutual gravity shreds their delicate structures. Gas clouds collide, triggering frenzied star birth until the fuel runs out, leaving behind a smooth, star-rich blob. The largest ellipticals often sit at the hearts of galaxy clusters, gorged on smaller neighbors over eons. But not all galaxies play by these rules. Irregular galaxies, like the Large Magellanic Cloud, are the cosmic misfits, asymmetrical, messy, and often rich in gas. Some were born this way, their gravity too weak to form orderly shapes. Others had their structures wrecked by gravitational encounters, like a comet passing too close to Jupiter. These galaxies are time capsules, showing what the early universe might have looked like before gravity smoothed things out. Dark matter's role in this cosmic sculpting remains a puzzle. Simulations suggest its invisible halos dictate how galaxies spin and clump, yet some ultra-diffuse galaxies, almost see-through with stars, seem to have hardly any dark matter at all. Then there's the missing satellite problem. Dwarf galaxies around the Milky Way are far fewer than dark matter models predict. Are our theories flawed, or have interactions erased these smaller galaxies over time? Every galaxy's shape is a fossil record of its history of collisions, star births, and the invisible hand of dark matter. As telescopes peer deeper into the cosmic dawn, they're catching galaxies in their infancy, revealing how these majestic structures emerge from the primordial dark. And with each discovery, we're decoding not just how galaxies look, but the hidden forces that mold them. In the constellation Cygnus, about 1,500 light-years away, there's a star that refuses to follow the rules. KZ 8462852, better known as Tabby's star, after astronomer Tabitha Boyajian, who first noticed its bizarre behavior, doesn't flicker like other stars. Instead, it plunges into dramatic, unpredictable dips in brightness, sometimes fading by up to 22% for days or weeks before snapping back to normal. No known natural phenomenon could explain such extreme dimming, which is why, for a brief moment, the world dared to wonder, had we found evidence of an alien megastructure? The idea wasn't entirely science fiction. In the 1960s, physicist Freeman Dyson theorized that advanced civilizations might build vast energy collecting arrays around their stars, swarms of mirrors, or solar panels known as Dyson spheres. When telescopes spotted Tabby's star's irregular light patterns, some researchers suggested we might be seeing fragmented sections of such a structure passing in front of the star, blocking its light in unnatural ways. The internet exploded with speculation, and even sober scientists admitted the data was weird enough to warrant consideration, but the universe rarely serves up simple answers. Follow-up observations revealed the star's infrared glow didn't match what a solid megastructure would produce. Instead, the dimming seemed to scatter light like fine dust. Further analysis pointed to a more mundane, yet still fascinating, explanation: colossal clouds of shattered planets or comets. Imagine a star surrounded by the wreckage of a cosmic demolition derby, giant fragments and pulverized rock trailing in chaotic orbits. As these debris clouds drift between us and the star, they'd blot out its light unevenly, creating the erratic dips we've observed, yet Tabby's star hasn't surrendered all its secrets. The dust theory explains some of the dimming, but not the star's century-long, gradual fading, something unprecedented in astronomical records. Some propose a recent planetary collision, like the one that gave Earth its moon, left the system shrouded in an expanding debris field. Others wonder if the star itself is unstable, prone to violent outbursts that belch dust into space, or perhaps it's something we haven't even imagined yet, a phenomenon that rewrites our understanding of stellar behavior. For now, Tabby's star remains a cosmic enigma, a reminder that the universe loves to tease us with mysteries just beyond our grasp. Whether it's alien engineering or an astronomical catastrophe, one thing's certain: this star's story is far from over. Turn the moon around in your mind. The face we see from Earth, with its dark patches and familiar man in the moon, is nothing like the far side, a jagged wilderness of craters and mountains. This lunar split personality isn't just a quirk, it's a puzzle that's baffled scientists for decades. The near side is dominated by vast, smooth plains called Maria, ancient lava flows that hardened into dark basins. But flip the coin, and the far side looks like it's been through a cosmic blender, with terrain so rough, it's practically unrecognizable as the same moon. The key to this mystery lies in the moon's violent youth. Billions of years ago, the inner solar system was a shooting gallery, with asteroids and protoplanets smashing into worlds still cooling from their formation. The moon took brutal hits, but the far side bore the brunt. Evidence suggests a colossal impactor, perhaps the size of a small planet, slammed into the moon's southern hemisphere early in its history, creating the South Pole Aitken Basin, one of the largest known craters in the solar system. The shockwaves from this cataclysm may have fractured the crust on the far side, making it thicker and more rigid, while the near side remained thinner and more prone to volcanic activity later on. Then there's Earth's gravitational tug. The moon is tidally locked, always showing us the same face, but that doesn't mean our planet's pull is uniform. Tidal forces heated the near side's interior, keeping it molten longer and allowing magma to seep through cracks, flooding basins with lava. The far side, shielded from this heat, stayed colder and more geologically stagnant, preserving its battered surface like a fossil record of primordial violence. But here's the twist: the far side isn't just thicker, it's also strangely lacking in the dark Maria that defined the near side. One theory points to radioactive elements. Samples from Apollo missions revealed the near side is richer in heat-producing elements like uranium and thorium, which could have fueled volcanic eruptions. If these elements were unevenly distributed during the moon's formation, it would explain why one side oozed lava while the other stayed frozen in time. The moon's dichotomy isn't just a scientific curiosity, it's a window into the chaos of the early solar system. Every crater, every ridge on that hidden face tells a story of bombardment and upheaval, a time when worlds were reshaped by forces we can barely imagine. And thanks to missions like China's Chang'e 4, which landed on the far side in 2019, we're finally starting to read that story firsthand. What we're learning might not just solve the riddle of the moon, it could rewrite what we know about how all rocky planets, including our own, came to be. Imagine a single object so bright, it outshines an entire galaxy, a cosmic lighthouse beaming across billions of light years. These are quasars, the most powerful engines in the universe, radiating energy equivalent to 1 trillion suns from a region no larger than our solar system. For decades after their discovery in the 1950s, quasars baffled astronomers. How could something so compact produce such mind-bending luminosity? The answer lies in the hungriest monsters in existence, supermassive black holes. At the heart of every quasar sits one of these gravitational behemoths, weighing anywhere from millions to billions of times the mass of our Sun. But a black hole alone doesn't shine, it's the frenzied feast surrounding it that lights up the cosmos. As gas, dust, and even whole stars spiral toward the event horizon, friction heats this material to millions of degrees, creating an accretion disk that glows with the fury of 100 supernovae. The disk acts like a cosmic particle accelerator, twisting magnetic fields into jets that shoot matter outward at nearly light speed, some spanning millions of light years. These jets, visible in radio waves, are the universe's largest natural blowtorches, yet the sheer efficiency of quasars defies intuition. Matter falling into a black hole shouldn't convert more than a fraction of its mass into energy, unless Einstein's E equals mc squared gets a cosmic cheat code. Enter the Penrose process, a trick where energy is extracted directly from a black hole's rotation. If the accretion disk spins in sync with the black hole, particles can steal rotational energy and escape as ultra-powerful radiation. Some quasars might harness this mechanism, turning spinning spacetime itself into a battery. Quasars aren't just relics of the past, they are snapshots of the universe's most violent adolescence. The brightest ones thrived 10 billion years ago, when galaxies were gas-rich and black holes gorged themselves unchecked. Today, most have dimmed as their fuel ran out, leaving behind dormant giants like Sagittarius, a star at our Milky Way center. But occasionally, we catch a nearby galaxy flickering back to life as fresh material tumbles toward its black hole, a reminder that these cosmic powerhouses aren't extinct, just waiting. The lingering mystery, how quasars ignite so quickly. Some were already shining brilliantly when the universe was less than 1 billion years old, leaving little time for their black holes to grow so massive. Did they form from direct collapse of primordial gas clouds, bypassing the star stage entirely, or did early black holes merge and feed at rates we've yet to imagine? Each quasar's light carries clues about the universe's wild youth, written in wavelengths we're only beginning to decode. What if our universe is just one page in an infinite cosmic library, surrounded by countless others with entirely different rules? The idea isn't science fiction, it's the multiverse hypothesis, a radical reimagining of reality that's gaining traction among physicists. Take bubble universes first. Picture the early cosmos as a boiling pot of water, where each bubble that forms is a new universe inflating rapidly, with its own unique physics. Some might have stronger gravity, others might lack electromagnetism entirely, wildly different worlds where matter never clumped into galaxies or atoms couldn't form. These bubbles aren't just theoretical, they emerge naturally from inflationary cosmology, the leading model of the Big Bang. Then there's string theory's landscape, a dizzying array of possible universes predicted by the mathematics of tiny, vibrating strings. The theory suggests there could be 10 to the 500 different vacuum states, each representing a distinct universe with its own constants and forces. In this view, our finely tuned cosmos, where stars burn and life exists, isn't special, just one lucky draw in a cosmic lottery. Some physicists argue this explains the anthropic principle. We observe these precise laws because, well, we couldn't exist in the universes where they're different. But the multiverse gets even stranger with quantum mechanics. The many worlds interpretation proposes that every quantum decision spawns a new timeline. Schrödinger's cat isn't just alive or dead, the universe splits, creating one reality for each outcome. While this seems outlandish, it solves the measurement problem. The observer's role in collapsing quantum states vanishes if every possibility plays out somewhere. So how do we test something so unfalsifiable? Surprisingly, there are clues. If our universe once collided with another, the cosmic microwave background might bear scars, anomalous cold spots, or swirling polarization patterns. Some researchers claim to have spotted these in satellite data, though skepticism remains. Others hunt for evidence in gravitational waves, which could carry echoes of pre-Big Bang events. And if string theory's extra dimensions exist, particle accelerators might one day reveal traces of interactions with parallel brain worlds. The multiverse stretches our imagination to the breaking point. It challenges not just what we know, but how we define reality itself. Whether it's true or not, the mere possibility forces us to confront a humbling thought. The greatest mystery of the cosmos might not be what's out there, but what's beyond there altogether. The universe is expanding, but where does that road ultimately lead? Depending on which cosmic clues you follow, the answer could be a slow fade into darkness, a violent collapse, or even a dramatic shredding of spacetime itself. The fate of everything hinges on a tug-of-war between dark energy, gravity, and the very fabric of reality. Let's start with the most widely accepted scenario, the heat death or big freeze. Picture trillions of years from now, as dark energy accelerates the expansion of space. Galaxies grow so distant, their light can no longer reach us. Stars exhaust their fuel, leaving behind cold husks, white dwarfs, neutron stars, black holes that gradually decay over incomprehensible timescales. Even black holes aren't eternal, they emit Hawking radiation, evaporating into nothingness over googles of years. Eventually, the universe reaches maximum entropy, a state where energy is uniformly distributed, every temperature equal, and no work can be done. It's not an explosion or a collapse, just an endless, silent night where time loses all meaning. But what if dark energy weakens or gravity gets the upper hand? That's where the big crunch comes in, a cosmic reversal where expansion halts and the universe collapses inward. Galaxies would rush toward each other as space contracts, temperatures soaring until atoms themselves unravel. The entire cosmos might compact into a singularity, perhaps triggering another Big Bang in a never-ending cycle. For this to happen, dark energy would need to fade, allowing gravity to pull everything back together. Yet current observations show the opposite. Expansion is speeding up, not slowing. Now for the most dramatic finale, the Big Rip. If dark energy grows stronger over time, it wouldn't just push galaxies apart, it would overpower every force holding them together. First, galaxy clusters would tear apart, then individual galaxies. Stars would be ripped from their orbits, planets from their suns. In the final moments, even atomic bonds would snap, reducing all matter to disconnected particles. Space itself would be shredded faster than light, leaving a void where nothing can ever interact again. The wild card, dark energy's nature, is still a mystery. Is it truly constant, as Einstein's cosmological constant suggests, or could it evolve? Some theories propose phantom energy, a form of dark energy that intensifies with time, making a big rip inevitable. Others suggest it might decay, flipping the script toward a big crunch. The fate of the universe isn't just academic, it's a countdown we're all part of, ticking toward an ending we can't yet predict. Venus should be Earth's twin, born from the same cosmic dust, orbiting in the same temperate zone of the solar system, even roughly the same size and composition. Yet stepping onto its surface would be like walking into a pressure cooker set to sulfuric acid mode. At 900 degrees Fahrenheit, it's hot enough to melt lead. The air is so thick, it feels like diving a kilometer underwater, and those beautiful clouds, they're not made of water vapor, but corrosive sulfuric acid rain that evaporates before it even hits the ground. How did two planets so similar become cosmic opposites? The answer lies in a runaway disaster that could have been Earth's fate too. Billions of years ago, Venus might have been downright pleasant shallow oceans, a temperate climate, maybe even the ingredients for life. But lurking in its rocks was a time bomb, carbon dioxide. On Earth, this greenhouse gas gets recycled through plate tectonics and absorbed by oceans, keeping our climate stable. Venus lacked that safety valve. As the young sun grew brighter, its warmth baked the planet's surface, releasing CO2 trapped in rocks. The more carbon dioxide filled the air, the hotter it got, which released even more CO2, a vicious cycle spinning out of control. With no oceans left to absorb it, the atmosphere became a suffocating blanket, turning Venus into a pressure cooker hellscape. Earth dodged this apocalypse by sheer luck. Our planet's slightly cooler position allowed water to persist, which dissolved CO2 and locked it away in carbonate rocks. Plate tectonics, Venus's missing ingredient, acted like a planetary thermostat, recycling carbon over eons. But the most chilling part, Venus's past might be Earth's future. As the sun ages, it's growing brighter. In a billion years, our oceans could boil away, triggering the same runaway greenhouse effect. The difference is, we're accelerating the process by pumping carbon into the air ourselves. Venus stands as a cautionary tale, a glimpse of what happens when a planet loses its balancing act. Yet mysteries linger. Why did Venus's volcanoes resurface the planet in massive lava floods instead of steady eruptions like Earth's? Why does its super-rotating atmosphere whip around the planet 60 times faster than the surface spins? And where did all its water go? Some scientists suspect solar winds, unimpeded by a magnetic field, stripped away hydrogen atoms molecule by molecule. Others think the oxygen bonded with rocks, leaving the planet bone dry. Every probe we send, from the Soviet Venera landers to NASA's upcoming Da Vinci mission, peels back another layer of this enigma. The story of Venus isn't just about a failed twin. It's a reminder of how fragile planetary equilibrium can be, and how small shifts can tip a world from paradise to inferno. Studying its scars might be the key to understanding not just our solar system's past, but Earth's own precarious future. Every second, trillions of invisible bullets rip through your body at nearly light-speed cosmic rays, high-energy particles from deep space that bombard Earth relentlessly. Some carry the energy of a fast-pitched baseball packed into a single atomic nucleus, yet their origins remain one of astrophysics' most enduring whodunits. The hunt begins with supernova stellar explosions so violent, they can sling charged particles across the galaxy like a cosmic pinball machine. When a massive star dies, its shockwaves accelerate protons and electrons to near light speeds, creating a soup of energetic particles we detect as cosmic rays. But there's a problem. While supernova explain some lower energy rays, the real monsters, ultra-high energy cosmic rays, pack millions of times more punch than anything a supernova could produce. These rare extreme particles smash into our atmosphere with the force of a bowling ball dropped from waist height, yet their sources lie outside our galaxy entirely. That's where active galactic nuclei come in. At the hearts of distant galaxies, supermassive black holes devour matter, spewing jets of plasma that could act as natural particle accelerators. Picture a cosmic hadron collider billions of light-years long, where magnetic fields whip particles to unimaginable speeds. Some rays might even come from colliding galaxy clusters or mysterious, dark matter annihilation, hypothetical events where invisible particles meet and annihilate in bursts of energy. Yet the mystery deepens when we track these particles back to their origins. Unlike light, cosmic rays are charged, meaning interstellar magnetic fields bend their paths into chaotic spirals, erasing their starting points. It's like trying to trace a ricocheting bullet blindfolded. The highest energy rays are so rare, we've detected fewer than 100 in a century, each one a cryptic postcard from the universe's most violent corners. The Pierre Auger Observatory in Argentina uses 1,600 giant water tanks spread over 3,000 square kilometers to catch these elusive messengers. When a cosmic ray hits the atmosphere, it creates a cascade of secondary particles that trigger the tanks like dominoes, but even this massive detector only catches a few ultra-high-energy events per year, and their arrival directions point frustratingly toward empty space. What's clear is that cosmic rays are more than just space weather. They've shaped life on Earth, possibly influencing cloud formation and even genetic mutations over evolutionary timescales. They're also a reminder that the universe is far wilder than it appears, a place where particles surf magnetic tsunamis across galaxies, and the most powerful accelerators aren't human-made, but forged in the chaos of black holes and dying stars. Until we solve their riddles, these invisible invaders will keep raining down, each one a whisper from the cosmos' darkest corners. We often think of space as an empty void, but it's far from featureless. Threaded through it are invisible lines of force that shape everything from planets to galaxies. Magnetic fields are the universe's hidden architects, sculpting cosmic dust into stars, shielding worlds from deadly radiation, and even launching jets of matter hundreds of thousands of light years into the void. Take Earth's magnetic field, our planet's silent guardian. Generated by the churning of molten iron in the core, this invisible shield deflects the solar wind, a relentless stream of charged particles from the sun. Without it, our atmosphere would slowly erode, stripped away like sand in a hurricane. Mars stands as a grim example. Once thought to have rivers and possibly even oceans, it lost its protective magnetic field billions of years ago, leaving it exposed and barren. But Earth's field isn't just a barrier, it's dynamic, shifting over time in ways that create the dazzling auroras near the poles, where solar particles slip through and ignite the sky. The influence of magnetism reaches far beyond our planet. Inside stellar nurseries, those dense clouds where stars are born, magnetic fields act like cosmic scaffolding. Without them, gas would collapse too quickly under gravity, forming chaotic clumps instead of stable stars. Instead, fields channel the flow of material, slowing the collapse and guiding it into spinning disks. These disks, called protoplanetary systems, eventually give rise to planets, their orbits shaped by the same magnetic forces that birth them. Some stars, particularly the highly magnetized ones called magnetars, take this to extremes. Their fields are so strong, they could wipe a credit card clean from halfway across the Milky Way. Then there are the enormous structures like the jets screaming from active galactic nuclei. At the center of many galaxies, supermassive black holes devour matter, but not all of it falls in. Some get swept up by magnetic fields into narrow, high-speed beams that shoot out across space, visible for millions of light years. These jets, glowing in radio waves, can sculpt entire galaxy clusters, heating surrounding gas and preventing it from cooling into new stars. Without magnetic fields, the universe would lack some of its most dramatic and beautiful phenomena. Yet for all their power, magnetic fields remain one of the least understood forces in cosmology. We still don't fully know how they first arose. Did they emerge from the turbulence of the early universe? Or were they seeded by quantum fluctuations in the Big Bang's aftermath? Even today, new discoveries challenge old assumptions. Recent observations of filaments in the cosmic web, the largest structures in the universe, suggest magnetic fields might stretch across these vast, thread-like formations, influencing how galaxies form and evolve. The deeper we look, the clearer it becomes. Magnetism isn't just a footnote in astrophysics, it's a fundamental force weaving order into the cosmic chaos. From the smallest plasma swirls to the grandest galactic designs, these invisible fields are the silent conductors of the universe's most spectacular symphonies. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1970s, they carried humanity's first messages to the stars' gold plaques, etched with symbols of our existence. But as these trailblazing probes sailed toward the outer solar system, something peculiar happened. They began slowing down ever so slightly, as if an invisible hand was tugging them backward. This tiny but persistent deviation, just 300 billionths of a meter per second squared, became known as the Pioneer anomaly, a cosmic glitch that had physicists scratching their heads for decades. At first glance, the numbers seemed trivial, but in the precision-driven world of orbital mechanics, even microscopic discrepancies can point to monumental gaps in our understanding. The probe's slowdown defied predictions based on known gravity and solar radiation pressure, sparking wild speculation. Could this be evidence of new physics, a hint of dark matter's gravitational pull, or even a flaw in Einstein's theory of relativity? Some theorists floated radical ideas, like modified inertia or the influence of higher dimensions, but before rewriting the textbooks, scientists had to consider a far more mundane possibility: heat. Pioneer's nuclear power sources constantly emitted warmth, and its asymmetric design meant more thermal radiation escaped from the back of the spacecraft than the front. This imbalance could have created a minuscule but measurable thrust in the opposite direction, like a car idling with one brake lightly engaged. Researchers painstakingly reconstructed decades-old engineering documents, even tracking down vintage thermal paint samples to model the effect. By 2012, their simulations confirmed that subtle photon recoil from the probe's radioactive decay heaters could account for most, if not all, of the anomaly. Case closed, not entirely. While thermal radiation explains the bulk of the slowdown, lingering questions remain. The probe's deceleration didn't perfectly match the heat models, leaving a tiny residual unaccounted for. Could there still be an undiscovered force at play, or does the discrepancy simply reveal gaps in our ability to model complex thermal emissions across interstellar distances? The debate crystallizes a fundamental challenge in physics, distinguishing between mundane measurement errors and genuine breakthroughs. Pioneer's legacy endures as a cautionary tale, reminder that the universe often hides its secrets in the smallest details. What began as a whisper of rebellion against known physics ultimately taught us to interrogate our assumptions, whether about spacecraft design or the fabric of reality itself. And while most scientists have moved on, a stubborn few still wonder, what if that faint, unexplained tug was the first hint of something far stranger, waiting to be uncovered in the dark? Mercury shouldn't make sense. This tiny world, barely larger than Earth's moon, somehow packs a core that takes up nearly 60% of its volume. For comparison, Earth's core only occupies about 15%. Why would a planet so small have such a bizarre, bloated metallic heart? The answer might lie in a catastrophic collision so violent, it rewired Mercury's entire structure. Imagine the early solar system, a chaotic construction zone where planets were still taking shape. Mercury, forming close to the Sun, was bombarded by debris. Then a rogue protoplanet, perhaps the size of Mars, slammed into it at thousands of miles per hour. The impact wouldn't just leave a crater, it could have vaporized much of Mercury's rocky outer layers, blasting them into space. What remained was a stripped-down version of the original planet, its once thick mantle reduced to a thin shell clinging to a disproportionately massive core. But the giant impact theory isn't the only explanation. Some scientists argue Mercury's composition might reflect its birthplace. Close to the Sun's scorching heat, only the densest materials, metals like iron and nickel, could have condensed and clumped together in the protoplanetary disk. Lighter elements, the building blocks of rocky mantles, might have been blown away by solar winds before they could accumulate. This scenario paints Mercury not as a scarred survivor, but as a cosmic high roller that formed in a metal-rich VIP zone. Then there's the slow cooker model. Intense heat from the young sun could have roasted Mercury's surface, vaporizing silicates and leaving behind a concentrated metallic core, like a cosmic reduction sauce. Over eons, this process might have left the planet denser than its neighbors without requiring a cataclysmic impact. NASA Messenger mission provided tantalizing clues. It detected low levels of iron-melting elements like sulfur on Mercury's surface, far lower than expected if the planet formed normally. A giant impact could have blasted these volatiles into space, while the solar vaporization theory struggles to explain their absence. Yet Mercury's magnetic field, detected by Messenger, suggests its core is still partly molten, an oddity for such a small world, hinting at complex internal dynamics we don't fully grasp. Mercury's oversized core isn't just a planetary oddity, it's a time capsule from the solar system's most violent era. Whether sculpted by collisions, forged in extreme heat, or born from unique chemistry, this tiny world forces us to question how planets are built. And with Europe's BP Colombo probe now orbiting Mercury, we might finally get answers or uncover even deeper mysteries lurking beneath that metal-rich shell. The moon's surface seems bone-dry, a barren desert where astronauts' footprints lie unchanged for decades, but hidden in its polar craters, where sunlight never reaches, lie vast reservoirs of ice. This frozen water is a scientific goldmine, but its origin is a puzzle. How did a world with no atmosphere and scorching temperature swings end up with pockets of ice? The answer might rewrite the moon's history and hint at how water arrived on Earth. One theory points to the solar wind, the constant stream of charged particles screaming from the sun. These particles, mostly protons, bombard the moon's surface, embedding hydrogen atoms in the lunar soil. Over billions of years, oxygen in the regolith could bond with this hydrogen, forming tiny amounts of water molecules. Laboratory experiments back this up. When simulated solar wind hits lunar soil, analogs trace water forms, but there's a catch. This process is achingly slow, and the water it creates is usually locked in minerals, not free ice. Could it really account for the thick ice sheets spotted by probes like NASA Lunar Reconnaissance Orbiter? That's where comets enter the story. These cosmic snowballs, rich in water ice, have pummeled the moon since its formation. When a comet strikes, most of its water vaporizes in the heat of impact, but some could get trapped in the frigid, shadowed craters near the poles, nature's deep freezers. India's Chandrayaan-1 mission found evidence of water molecules clinging to the surface, and Alcross, a NASA impactor, kicked up plumes containing water vapor when it slammed into a lunar crater into the Nine. The chemistry of that water held clues. Its isotopic ratios, its unique flavor, seem to match certain comets, bolstering the icy impactor theory, but the plot thickens with another suspect, ancient lunar volcanism. Billions of years ago, the moon was geologically active, spewing lava from massive eruptions. These fiery outpourings might have released water vapor trapped in the moon's mantle. Some of that vapor could have migrated to the poles, condensing as frost in the eternal shadows. Support for this idea comes from volcanic glass beads brought back by Apollo astronauts in tiny time capsules containing trace water. If the young moon was wetter inside than we thought, its volcanic belches might have seeded the poles with ice long after its surface hardened. The truth might be all three, a cocktail of solar wind, cometary deliveries, and volcanic whispers. Each source leaves a distinct fingerprint in the ice's chemistry, and future missions like NASA Viper rover aim to taste those differences firsthand. But the implications stretch beyond the moon. If water arrived here via comets or solar wind, the same could be true for Earth and for other seemingly dry worlds like Mercury or asteroids. The moon's hidden ice isn't just a curiosity, it's a time capsule holding clues to how water, the essence of life, journeys through the cosmos. The magnetic field around a typical neutron star is already mind-bending, strong enough to warp the electron clouds in your body from thousands of kilometers away. But magnetars take this to another level entirely. These cosmic monsters boast fields 1,000 times more intense than their neutron star cousins, reaching strengths of 10 to the 15th Gauss. To put that in perspective, if a magnetar appeared halfway between Earth and the moon, its magnetic pull would erase the data from every credit card on the planet. So how does a dying star become such a magnetic powerhouse? It starts with the violent death of a massive star in a supernova. As the core collapses, three crucial ingredients: rapid rotation, turbulent convection, and quantum weirdness combine to amplify magnetic fields to ludicrous extremes. Imagine a spinning ball of liquid iron the size of a city, churning like a hurricane. Electrons and protons in this soup get twisted into colossal electric currents, which generate magnetic fields through something called the dynamo effect. In most neutron stars, this process settles down after a few seconds, but in magnetars, the chaos persists long enough to crank the magnetic dial to 11. These fields don't just sit there quietly, they're under constant strain, locked in a battle with the star's rigid crust. When the crust can't take the stress anymore, crack. A starquake occurs, the cosmic equivalent of a tectonic slip but with universe-shaking consequences. The crust fractures, releasing pent-up energy in milliseconds, triggering gamma-ray flares brighter than 100,000 suns. In 2004, a magnetar 50,000 light-years away unleashed a blast so powerful, it temporarily ionized Earth's upper atmosphere despite being located on the far side of our galaxy. Yet the real mystery isn't just the strength of these fields, but their stability. Quantum mechanics suggests fields this strong should decay almost instantly as particles realign to lower energy states. But magnetars defy this, maintaining their ferocious magnetism for centuries. One theory points to superconducting protons in the core, where frictionless currents could sustain the field indefinitely. Others propose exotic particles like hyperins or quark matter might be propping it up. The universe rarely does anything without a reason. Magnetars might be nature's way of showing us physics at its most extreme, a laboratory where matter, energy, and magnetism collide under conditions we can't begin to replicate on Earth. Every flare, every starquake is a message in a bottle, sent from the edge of what's possible. And as we decode these signals, we're not just learning about stars, we're uncovering the hidden rules that govern all magnetic phenomena, from the smallest atoms to the largest structures in the cosmos. Beyond Neptune's orbit, the solar system doesn't just fade quietly into darkness, it drops off a cliff. Astronomers call it the Kuiper Cliff, a bizarre boundary around 50 astronomical units out where the number of icy objects doesn't gradually taper off as you'd expect, it plunges. One moment you're counting hundreds of frozen leftovers from the solar system's birth, and the next, it's like someone flipped a switch. This isn't just a statistical fluke, it's as if something swept the outer reaches clean or corralled everything inward, leaving a cosmic no man's land beyond. The simplest explanation: a hidden planet, not just any planet, something massive enough to gravitationally shepherd the Kuiper belt's outer edge. Picture a world several times heavier than Earth, lurking so far from the Sun that its orbit could take 20,000 years to complete. At that distance, even a Jupiter-sized object would reflect so little sunlight, our telescopes might miss it entirely, but its gravity would leave fingerprints, tugging distant objects into peculiar clusters, or clearing a path like a snowplow through the icy debris. Some researchers point to strange alignments in the orbits of extreme trans-Neptunian objects, all tilted in similar directions, as evidence of this unseen puppeteer, the same clues that fueled the Planet 9 hypothesis. But the Kuiper Cliff might not need a planet at all. Rewind the clock 4.5 billion years, and the early solar system was a demolition derby of protoplanets. A close pass by a rogue star, or the gravitational jostling of a since-ejected ice giant, could have yanked countless objects inward or slingshotted them into interstellar space. Alternatively, the young sun might have been born in a dense stellar nursery, where neighboring stars stripped away our outer debris like thieves in the night. These primordial disruptions would have left behind a sharp edge, a fossilized boundary etched by chaos. Then there's the wild card: radiation pressure. The sun's ultraviolet light can push tiny ice particles outward over eons, while larger objects stay put. This sorting process might create an invisible sieve, leaving only bigger bodies beyond a certain distance. But that doesn't explain why even mid-size Kuiper belt objects vanish so abruptly. Every probe we send to the outer solar system, from New Horizons' dash past Arakoth to future missions eyeing Uranus, brings us closer to solving this riddle. Until then, the Kuiper cliff stands as a silent sentinel, guarding secrets about our solar system's violent youth and the unseen forces that might still shape its fringes. Whether it's a hidden world, ancient upheaval, or something even stranger, one thing's clear: the universe hates a vacuum, especially at its edges. The sun plays a cruel cosmic joke on anyone trying to understand its physics. While its surface simmers at a cool 5,500 degrees Celsius, just above it lies the corona, a wispy halo of plasma burning at over 1,000,000 degrees. It's like stepping away from a campfire and somehow getting scorched by the empty air around it. This temperature inversion defies everything we know about heat, and unraveling this mystery has forced scientists to rethink how energy travels through the universe. At the heart of the puzzle is the sun's magnetic field, a tangled web of invisible lines that twist and snap like overstretched rubber bands. When these field lines cross or reconnect, they release colossal bursts of energy in a process called magnetic reconnection. Picture two rubber bands under tension suddenly breaking and reattaching to each other. The snap unleashes stored energy as heat. On the sun, this phenomenon accelerates particles to insane speeds, superheating the corona's thin plasma. NASA Parker's solar probe, which flies closer to the sun than any spacecraft before it, has detected nanoflares, tiny explosions from these reconnection events, that collectively could explain the corona's extreme temperatures. But magnetic reconnection isn't the only suspect. Alfvén waves, named after Nobel laureate Hans Alfvén, might also be pumping heat into the corona. These are ripples in the sun's magnetic field, generated by convective turbulence below the surface. Like ocean waves crashing onto a shore, they carry energy upward, where it dissipates as heat. Some observations show these waves traveling at speeds over 1,000,000 miles per hour, fast enough to deliver the energy needed to roast the corona, yet critics argue their contribution might be too small to account for the full temperature gap, leaving room for other players. Then there's the role of solar wind. The corona doesn't just sit there, it's constantly streaming outward as a supersonic flow of charged particles. This escaping plasma might act like a radiator, carrying away heat in a way that local heating mechanisms can't fully explain. The interplay between confinement and escape could be key, like a pot with a lid that's slightly ajar, allowing just enough steam to vent while keeping things boiling inside. The corona's heat isn't just an academic curiosity. It drives solar storms that can knock out satellites and power grids, and understanding it could unlock secrets of other stars, or even fusion energy here on Earth. Every new observation peels back another layer, revealing a sun that's far more dynamic and enigmatic than we ever imagined. So while the corona's blistering temperatures still perplex us, they're also a blazing reminder of how much we have yet to learn about the forces shaping our cosmic neighborhood. Stephen Hawking's most shocking discovery wasn't about what black holes consume, it was about what they supposedly erase. When particles escape through Hawking radiation, they appear to carry away mass and energy, but what about the information that fell in? Quantum mechanics insists information can never truly vanish, yet black holes seem to be cosmic shredders, permanently deleting the blueprints of anything they swallow. This paradox pits two pillars of physics, general relativity and quantum theory, against each other in a battle with universe-shaking stakes. Imagine tossing a book into a fire. The pages burn to ash, but in principle, every word could be reconstructed from the smoke's chemistry and the heat's patterns. Now imagine throwing that book into a black hole. According to Hawking's early work, the radiation leaking out would be completely random, a featureless thermal glow with no ties to the book's contents. The information would be scrambled beyond recovery, violating quantum mechanics' sacred principle of unitarity, which states every particle's history must be traceable through time. Physicists called this the information paradox, and it sparked a decades-long war of ideas. One camp, led by Hawking himself for years, argued information truly vanishes, that black holes rewrite the rules of reality at their singularities. This horrified quantum theorists, who saw it as scientific heresy. Then came the counterattack, the holographic principle, proposed by Gerard T. Hooft and Leonard Susskind. This radical idea suggests all information falling into a black hole gets smeared across its event horizon, like a cosmic etch-a-sketch. The surface area, not the volume, encodes everything inside, meaning the book isn't lost, just projected onto a 2D boundary in quantum pixels. Hawking radiation, then, wouldn't be random but a slow, encrypted playback of that data. But how does this actually work? Enter quantum entanglement. When particle pairs pop into existence near the horizon, one falling in, one escaping, their quantum states remain linked. The escaping particle might carry information about its trapped twin, effectively telegraphing the interior's secrets to the outside universe. Over time, as the black hole evaporates, all the original information could theoretically leak out, reassembled in the radiation like a jigsaw puzzle. The plot thickens with firewalls, a nightmare scenario where the event horizon becomes a ring of searing particles, destroying anything crossing it. Born from attempts to preserve information, this idea suggests violent quantum effects would incinerate an astronaut before they notice the horizon. It's a cure potentially worse than the disease, undermining Einstein's smooth spacetime vision. String theorists offer another escape route. Black holes might be fuzzballs, tangled yarns of energy strings with no sharp horizon. Information would stay trapped in these knots, leaking slowly but never erased. Meanwhile, loop quantum gravity posits black holes crunch into Planck star remnants, ultra-dense kernels that bounce back, preserving information in their quantum structure. The debate isn't academic. If black holes delete information, our universe's history is written in disappearing ink. Every supernova, every galaxy, every civilization's legacy could dissolve into randomness over eons. But if they preserve it even partially, then reality might be a cosmic ledger where nothing is ever truly forgotten, just transformed. The irony, we might never know for sure without diving into a black hole ourselves, a one-way trip where the answers, like everything else, could be just beyond our reach. From the ghostly pull of dark matter to the fiery enigma of the solar corona, these 30 questions aren't just gaps in our knowledge, they're invitations to discovery. Every time science hits a wall, it's not the end of exploration, it's the spark for a revolution. Think about it, without the mystery of Mercury's oversized core, we might never have uncovered the violent chaos of the early solar system. Without the eerie silence of the Fermi paradox, we wouldn't be questioning our place in the cosmos with such urgency. These puzzles aren't roadblocks, they're the universe's way of keeping us curious, pushing telescopes, probes, and human imagination to their limits. And here's the beautiful part, you don't need a lab coat to join the hunt. The next breakthrough could come from a backyard astronomer spotting an anomaly, or a high school student crunching data in their bedroom. Science thrives on collective wonder, and every time someone gazes at the night sky and asks, why, that's progress, so keep questioning. Share your favorite cosmic head-scratcher in the comments. Is it the great attractor's hidden grip, or the quantum whispers inside black holes? The universe loves a good mystery, and so do we. If these questions left you hungry for more, hit subscribe. We're just getting started. There are black holes to weigh, multiverses to debate, and maybe, just maybe, aliens to find. The cosmos is vast, unpredictable, and far weirder than fiction, and while we may never answer all 30 of these questions, the pursuit itself, that's how we turn the impossible into tomorrow's textbook chapter. Stay curious, the next great discovery might have your name on it.